Hi there. Uh, in this session, I will explain to you about vectors, and this lesson is parallel to uh, Extended Math IGCSE and also Core. Okay. So let's take a look at the objective first. Okay, the first one belongs to Core. So in vectors, Core students will be learning up until vector multiplication by scalar. Okay? Whereas extended math, you will need to cover all of these objectives. So again, keep in mind for core students, you only do until vector multiplication by a scalar. Right? Let's carry on. Let's start by a definition. Vector is a quantity, and when we talk about a quantity, there are two kind of quantities. The common one is scalar. Scalar is just a quantity or just a number, okay, such as temperature. Okay, when you're asked about the temperature, you can say 13 degrees, 20 degrees. So it's just a number. Similarly, with your age, 17 years old, 15 years old, so only a number. So a scalar is uh, is anything that can be described by a number. The second one is a vector. A vector needs a direction for it to make sense. So vector needs direction. Okay, so it has both the size or magnitude and direction. For examples, velocity. Velocity is a vector, and velocity consists of speed and direction. For example, wind velocity, say 20 kilometers per hour to the east. So this is uh, the size or magnitude, and this being the direction. Another example is displacement. Displacement is a vector. Okay, it consists of distance and direction. Okay, so for example, displacement of Kelapa Gading from Rawamangun is about 5 kilometers to the north. So those are simple examples of vectors. So you can say that vectors are directed quantities. Okay. So how do we represent vectors? Uh, we can represent vectors by a straight line. Okay. Straight line with an arrow which shows direction. But what about the size? Well, in this case, the size would be the length of this line, right? Also, we can use column to represent vectors. For example, 3, 1. The top one being the horizontal direction, the bottom one being the vertical direction. In this case, since this is positive, so 3 units to the right, and this is 1 unit up, and this is our vector. Okay, so vector can be represented by a straight line, like so, or by a column. Yeah. Right, so just to recap, in a column notation, the top one shows horizontal direction. Positive means right movement, negative means left movement, and the bottom ones indicates vertical direction. Okay. Positive means going up, negative means going down. All right. I will do just some of this exercise. Okay. Let's start off with A. Take a look at vector A. Vector A consists of one unit to the right and 3 units up. Therefore, vector A is equal to 1, 3. So 1, 3. Okay. Similarly with B, vector B. Vector B is equal to 1, 2, 3, 4, 5. 5 units to the right and 1 unit up. There you go. Okay, so vector B is equal to 5, 1. Similarly to vector C. Okay, vector C consists of 1 unit to the, sorry, 2 units. 2 units to the right, 1, 2, and 3 units down, so that has to be negative. So 2, negative 3. Okay, same thing goes to vector D, vector E, okay, and also vector F. Well, vector F, yes, vector F means 1 unit to the left, 1 unit up, so negative 1, 1. Okay, vector G is a bit different because there's no horizontal movement. Therefore, horizontal movement is 0. And then it moved downward by 3 units. 1, 2, 3. So 0, negative 3. Okay. Right. Again, just part of the vector representation. Vector represented by a lowercase letter. Okay. But the vertices are represented by uppercase letter. Right. And there are 3 ways to represent a vector. Okay. A lowercase written in bold, or a lowercase with an underbar, or you write the vertices in the, say, x, z. So vector x, z with arrow on the top. So that's how we write vectors. Okay. Right, just to recap again. So this is the common notation for vectors. This is vector A, B, means going from A to B. Okay, you write uppercase A, B with arrow on the top. Or you can write a lowercase, the bold one, okay, a thick lowercase, or just a lowercase with a bar underneath. So that's how we represent vector. Right, let's take a look at some properties. Vectors with the same magnitude and direction are equal. So take a look at these 2 arrows. They're both going to the same direction and they're both having equal length. So they are considered as equal vectors. If vectors have the same size and opposite direction, then you have to consider the negative notation. Such in this case, vector AB is equal to vector A, then vector BA is the opposite, so you put negative, so that's negative vector A. Okay. Okay, take a look at this. This is vector A, which is equal to 3 units to the right, so 1, 2, 3, and 5 units up, so 3, 5. So the opposite of vector A is equal to, you have to multiply vector A by negative notation, that become, or negative 1, and that become negative 3, negative 5. There you go. Okay, very simple. So instead of going 3 units to the right, you go 3 units to the left. And instead of going 5 units up, you go 5 units down. Okay? So you reverse the direction. Right, vectors, uh, even though they are put in different places, okay, as long as they're of the same size and direction, they remain the same. So this vector A just equal to that vector A because they're all the same, even though the locations are different. Okay. Right. Okay, let's consider these two vectors. Vector A is equal to 3, 5, 3, 5, and vector B is 4, 4, 4 unit down, okay, 4, negative 4. Then this vector here is equal to 2 times vector A, because we have 3 units to the right and 10 units up. Same thing with this. This is the opposite of vector B. So you write negative B. What about this one here? This is half B, because we have 2 units to the right and 2 units down. We know that vector B is equal to 4 minus 4. If you divide each component by 2, you end up with 2, negative 2. So that's 2, negative 2. Okay. This one is just the same as vector B, same direction, same size as well. This one is the opposite of this vector here. So negative 2A, or vector A. Right. That brings you to the next properties. If different size vectors have the same direction, they are scalar multiple of each other, just like in this case, vector A and vector 2A. Okay? They are both in the same direction, vector A and vector 2A, so they are multiple of each other. Okay? So say we have two vectors, vector M and vector N. So vector M is equal to K. K is just a scalar or number multiplied by N. Well, as you can see, vector M is equal to twice of vector N. So we can write M is equal to 2 times vector N. So again, if different sized vectors have the same direction, then they must be scalar multiples of each other. Okay. I hope you got the idea. Right. Next, we can perform algebraic operation in vector, but I will start off with the scalar multiplication, because we did scalar multiplication in the previous slides. So if you have 3 times vector b, that's just equal to b plus b plus b. Okay, just like in the common algebraic or common math operation. And in column vector, if you multiply that the x and y component by a number, say n, that's just equal to n multiplied by c and n multiplied by d. Okay, right. So say here we have vector a, and this is vector 2a, and just like in the previous slide, if you have vector 2a, you multiply 2 to each component in vector a, so that's give you 8, 6. And if you observe these two vectors, what's considered the same? in these two vectors? Well, obviously, they both have the same direction or parallel. And what is considered different? Well, obviously, the size or magnitude. Okay, so that's why whenever you have uh, two vectors of different length but of the same direction, so they are scalar they are scalar multiple of each other. Okay, right, let's talk about resultant. Okay, just remember in the earlier slide regarding vector representation, so a vector consists of horizontal component and vertical component, and that vector there is called the resultant. So resultant is a single vector which is equivalent to a set of vector. Okay, so one vector consists of uh, several components. For example, we have vector A plus vector B that give us vector C, and vector C is the resultant. It consists of vector A and vector B. Okay, so you can say that vector C is equal to vector A plus vector B. We will cover addition and subtraction a little later. Okay, and that also means it can be the reverse, meaning resultant can be broken down into components. So this is vector A, consists of x direction, x movement in the horizontal direction, and y movement, meaning vertical movement. Okay, right. So just to recap, this relate well to the resultant concept. Vectors can be rewritten in terms of other vectors. Here, vector C is equal to vector A plus vector B. Okay, so vectors can be rewritten in terms of other vectors. And that brings us to the vector addition. Let's consider two random vectors. And when we add them together, here we use tail to tip method. Okay, so say vector C is equal to vector A plus vector B. So you write the first vector, in this case vector A. Sorry, you draw the first vector, in this case vector A, and then you draw the second vector, vector B, starting from the tip of vector A, and then you draw the resultant beginning from the tail of vector A to the tip of vector B. Okay, there you go. That's how you do it. And we call this method again tail to tip. Right, I hope you get the idea. Okay, next question. If we do addition, A plus B, will it be similar to B plus A? So that's basically what this question is saying. So let's check. Okay, here we start off with vector B followed by vector A. Okay, again we start off with B and A, and the green one is the resultant. So what if we start off with A first followed by B? Again, we start with A first in this case and then followed by B. They they both give the same result, the same resultant. Therefore, it doesn't matter if we change the order of addition, because a plus b is just equal to b plus a in vector. So just like in the common mathematical operation. Yep. So a plus b is just the same as b plus a. Okay, so let's just put some numbers into the vectors. So say we have vector a is equal to 3, 5, and vector b is equal to 4, negative 4. If we add them, okay, we will get 7, 1. Okay, 1, 2, 3, 4, 5, 6, 7, and 7 to the right and 7 unit up. Okay, there you go. That's a plus b. So now let's do b plus a. Okay. So since we do b plus a, the result is also the same, which is equal to 7, 1. So it doesn't matter, yeah, because a plus b is just the same as b plus a. Okay. Just some note, if you do b plus a, then you draw b first, followed by vector a. Yeah. What about subtraction? In subtraction, what you do is you add the negative of that vector. Okay. So for example, if you are given this expression here, vector d is equal to vector a minus b. By the way, these should be lower cases, yeah? Again, these should be lower cases. Okay. So vector a and subtracted by vector b. So what you do is you add that with the opposite of vector b, right? So vector b goes that way, negative vector b goes this way. Okay, so you do a minus b give you vector d. Same thing with this example over here. If you do a plus b, vector a plus vector b, you get this resultant. But if you do subtraction, you do vector a minus vector b, and then you get this resultant instead. Okay. Right, let's do a couple of examples, or several examples rather, sorry. Okay, take a look at vector OB. This is vector OB. Vector OB, that's equal to vector A plus B, like so. Okay. But what about vector OY? This from O to Y. We have vector A, and we also have 2B. So OY is equal to A plus 2B. What about vector AX? So from A to X. So again, from A to X, you have vector B. And since we are going the opposite, this becomes minus 2C. Okay, minus vector to C. Okay, what about XO? So XO, again, we're going from X to O. So that's equal to vector to C minus vector B, because we're going the opposite, and then minus vector A. Okay, so again, if we go the opposite, we have to change the sign, and same thing with vector Y, X. Okay. Right, let's take a look at this example. Okay, take vector BA, or this should be easy. BA goes to the opposite of vector A, so that should be equal to negative vector A, or negative A. Okay, same thing with vector CB. Vector CB goes the opposite of vector B, so that's equal to negative vector B. Same thing with vector DC. Okay. Now let's take a look at vector AC. That's vector AC consists of A and B, so that's equal to vector A plus vector B, right? And AD is just equal to vector A plus vector B plus vector C. Okay, very straightforward. Okay. Okay, this one I will show you the answer, and then you can study by rewatching this video again. Okay, I'll just go through it quickly, and you can rewatch the video again. Okay. Right. Now this is a bit challenging. Okay, let's take a look. The instruction is similar to the previous two examples. You are asked to rewrite the following vectors in terms of A and B, or in terms of vector A and vector B. This means that your answer must consist of vector A and vector B. Okay, let's take a look at AP. Oh, by the way, when you see this notation here, that notation there, it divides a segment into equal size. So this means that this side, or this segment here, okay, QN is equal to PN, and this one here, OA, is equal to PA. Okay, so this segment is equal to this segment. Okay, let's make a start. Vector AP. So this should be obvious. Vector AP, since this size is equal to that size there, so that has to equal A. And what about AB? AB. So vector AB has to be minus A plus B, or B minus A. What about OQ? Okay, let's take a look at OQ. OQ is just twice a vector B. Okay, so that's equal to vector 2B. And PO, let's take a look at PO. That one there, from P to O, which is twice of vector A, but going the opposite direction. So we need to add negative. So negative vector to A. And moving on to PQ. Okay, vector PQ is equal to 2B minus 2A. Okay, because if you look at this, vector PQ is equal to, this is 2A, but negative because we are going the opposite direction. So negative vector 2A plus vector 2B. So that's equal to 2B minus 2A. Next, you are asked to find Pn, vector Pn. Now, vector Pn is just half of PQ. So you divide this by 2. So you should be getting b minus a. Okay, so you go negative a and then b, and that gives you vector Pn. But by that saying, this this here, this part here is equal to vector b. Again, this part here, if you connect that point there to that point there, that's equal to vector b. And we know that from here, pq divided by 2 give us b minus a. So this is minus a and b. Therefore, this line here is equal to vector b, right? Let's take a look at vector on. Okay, well, vector on is equal to vector a plus, well, again, as I mentioned just now, this is equal to vector b. Okay, and then vector an is equal to b, okay, because that's equal to, this part here is equal to vector b, as I mentioned just now. Okay, and bp is just equal to negative vector b, so you go that way, plus vector 2a. Okay, and last one is vector qa. Okay, that's equal to vector a minus vector 2b, because you go from q the opposite direction, so that's negative vector 2b, and that's just vector a. Okay, so there you go. Simple concepts about vectors and some mathematical operation that involve vectors. I hope you can follow. Thank you very much. Take care.